the birth of Southern Alps of New Zealand. Last stage of New Zealand geological formation, how we know today. In the previous series of videos about geology of Southern Alps, of South Island of New Zealand, we looked at how the New Zealand was built, from the material eroded away from Gondwana, brought to the ocean, built up from volcanic eruption, and then brought together to build the base of New Zealand. In this video, we'll look at the last stages of formation of Southern Alps of New Zealand till the present moment. During the first part of the Cretaceous, Rangitata uplift come to the end, and New Zealand region was mountainous and probably even higher than today. The mountains were made from the same turtleless rocks as today's Southern Alps, so the view was approximately similar like we've seen today in the South Island. Thus, at the end of Rangitata Orogeny 100 million years ago, New Zealand was a large area stretching several thousand kilometers along the eastern margin of Gondwana. Everything since we know is the late Cretaceous in Tertiary strata. However, most of these rocks were eroded. We can find isolated pockets of this material and reconstruct the story of formation of Southern Alps. In the early Cretaceous, there was not much material accumulated at that time. Most of the ancestral New Zealand was above the sea level and eroding away. This rock they deposited at that time could be found only around the east coast of New Zealand. The material had been accumulated during the dying phases of seafloor spreading. At that time, the erosion took over, and by the Middle Cretaceous, the mountains have been worn down to form extensive lowlands. There was numerous rivers flowing around the fertile plains, covering with vegetation. That's the time when the most of the coal will be formed and buried around Otago and Southland. Some of the remnants of vegetation found in that coal and between sandstone-mudstone sandwiches they preserved within show microscopic fossils and pollens, spores from plants that grew at the time in New Zealand. We know there was a lot of conifers, ferns and flowering plants, which were found across the whole Earth at that time. The time still dominated dinosaurs, and the fossils were even found in New Zealand. We find some fragments of the bones. In particular, we know that pterosaurs, flying reptiles, were present in New Zealand, and the sea dinosaurs such as plesiosaur and mosasaur were present around New Zealand. Majority of that material that were removed from the continent were moved towards the ocean. And we find in the east side of the country some remnants of that material deposits. We can find some pockets of grey mudstones and sandstones very similar to the turtleless rocks. We can differentiate it with Rangitata deposits by presence of these fossils, and they tell us not just the age of the material, but also information about the sea life, who was living at that time in the ocean. Numerous mollusks, fish, squid-like animals, and ammonites. There was also many marine reptiles, and we find the remnants of them in eastern Otago, North Canterbury, Marlborough, and Hawke's Bay. At the time the erosion was reshaping the Rangitata landmass during the Cretaceous and make it flat. At that time, about 100 million years ago, the whole region was starting to be pulled apart in the east-west direction. There was big cracks developing in the crust, and a break-off happened. And the numerous eruptions of new volcanoes was indication of new breakup. We can find some remnants of it in Canterbury and Marlborough. The major split began, and the land started moving again. The ancient New Zealand began to separate slowly from Gondwana, while the magma welled up within the rift. At that time, the ocean flooded into the space opening between, and the Tasman Sea was born. We talk about this stage more in detail in the video on the example of the Castle Hill rock basin. Watch my previous video about that. 85 million years ago, the sea floor spreading was fully on the way. New Zealand started moving towards the Pacific. By the time of 65 million years ago, the land had been largely reduced to low plains. In some parts, in central Otago and northwest Nelson, we could still see the surface of the old, flat Cretaceous landscape. Softer rocks were laid down on top during the Tertiary, but they were later stripped away to reveal the extensive flat area of hard basement rock. We call it Cretaceous peneplain. After New Zealand became independent from Gondwana, it's moved further and further from the subduction zone. As a result, the crust slowly began to cool and contract, become denser and sinking into the lithosphere. 30 million years ago, during the Tertiary period, the land started slowly sinking into the ocean. And by the middle of Tertiary, not that much of New Zealand left above the ocean. That time we know as the period of large accumulation of material all around New Zealand, not much of which actually preserved right now, only some pockets around the country. Watch my video about Castle Hill Basin. Most of this material you can find around the North Island and the pockets of preserved by the uplifting of the mountains in southern Alps, where this tertiary sediment was kind of like a sandwich, protected from the erosion within the basins. Castle Hill, Arthur's Pass are the good examples of that. Studying these deposits, the scientists reconstruct the temperature and environment, life and vegetation at that time around New Zealand area. After this period, Oligocene, about 35 million years ago, this process all continues, and by the 35 million years ago, middle of Oligocene, New Zealand looked like just a chain of small islands. After that, the shoreline around New Zealand began to pull back from the land. New shore sediment became deposited further and further out as new land emerged. By the Pliocene, about 5 million years ago, large areas of land had risen from the sea. The big event with major proportions was beginning. This major event with a huge proportions started to affect New Zealand crust, and the new uplift has started. This last 5 millions, we have the new stage of mountain formation, which continues right now. We call it Kaikoura Orogeny, after the Kaikoura range around the southern Alps. And the main feature of this mountain building, it's the Alpine Fault, the feature that helps us to reconstruct, like jigsaw puzzle, the events, how material was shifted, where, which end up being in today's position. South Island been split in two by the Alpine Fault. You can see it very well on the old satellite images, like very striking straight line. And this split start moving two parts relative to one another. If we shifted this two piece of land back about 480 kilometers, we can match the pieces of the strata back together, and we see this offset happened during the last 25 million years. That's how much movement happened along the Alpine Fault. So how it's happening, how the material was moved along the fault, building mountains. To answer this question, let's look on the ocean floor. On the east of the New Zealand, there's a big mid-oceanic ridge that extends thousands of kilometers along the floor of the South Pacific Ocean. Constantly new crust, oceanic crust in this case, being constantly generated, and the ridges moving away on both sides. East of the ridge, the crust is traveling towards the coast of South America, and it's diving into the subduction zone, one of the biggest on our planet. On the other side, one piece of the Pacific plate is moving west towards the Australian plate. New Zealand located right in the zone where these two plates collide. If you're looking again on this bathymetry map of the ocean floor, you see the line along which collision is taking place north of New Zealand. We call that area Kermadec Trench. It's the place where oceanic crust of the Pacific plate is subducted beneath oceanic crust of the Australian plate. And there's also numerous volcanoes associated with that. Near East Cape, the Kermadec Trench merged into another subduction trench, the Hikurangi Throw, which ran east of the Hawke's Bay and Wairarapa, and that place oceanic crust meets the continental crust. and it's subducted beneath the North Island. Thus, the North Island, numerous volcanoes been fed by the material which rising from the underneath in that area, and we know them like famous Tongariro, Nauruhoe, Ruapehu, Rotorua, Tarawera and White Islands in the Bay of Plenty, and also the Lake Taupo, part of the volcanic zone, and it represents huge, massive explosive volcano, one of the biggest in the history of humanity. From around area of Kaikoura south, the collision become more complicated, and both plates are made of continental crust. The continental crust not trying to slide one under another, and instead they just collide towards each other, and the Pacific plate suffer more and been squeezed more than Australian part, and it's scrambled and pushed up to build the mountains. The entire land composed of numerous cracks, we call them faults, and the largest one, of course, the Alpine Fault. This Alpine Fault directly divided Pacific and Australian plates. In the South Island, we find numerous fault systems because of that, which accommodate this pressure from the Alpine Fault. Even today, we keep discovering new faults all around. Pacific and Australian plates are sliding past one another, the crust on the west side moving north relative to the east side. The side-wave movements is evident from the air, and if you match the rivers and some valleys, you can see exactly how it's moving recently. Alpine Fault exits the coast in Fjordland, and southwards from here movement between the plates is transferred back to the subduction zone. Here the subduction faces the opposite direction, with oceanic crust of the Australian plate descending beneath continental crust of the Pacific. That's in general the layout of the main faults and trenches around New Zealand, explaining where we can find which type of material and where the main movements are occurring. Let's then talk about what's happening since 25 million years ago this collision started. A lot of basalt has recorded the movement along these plates, and geologists can reconstruct it, the direction and timing of this sliding. If you look closely into a plate tectonics video, I talked about mid-oceanic ridges and how by studying the magnetism of the basalts we can time and reconstruct not just the direction but also the rates of the movement and building of the oceanic crust. Thus, let's have a look. 25 million years ago, Pacific plate began to collide with Australian plate, and subduction zone developed to the northeast of New Zealand. Continental crust prevented subduction zone to extend, and the crust began to compress and fracture, forming a major transfer fault, Alpine Fault. 10 million years ago, movement on the Alpine Fault was tearing the New Zealand crust apart. Rocks were displaced, Pacific plate was advancing west, and all of the New Zealand region was being compressed. About 5 million years ago, New Zealand more or less started looking like today. Continental crust started narrowed in width and was crumbled up. Mountains were pushed up rapidly. East of the Alpine Fault, material started moving anti-clockwise and crashing into the Australian plate, pushing up the Southern Alps. At that time, we have those faults developing south of the Alpine Fault. Today, we see the subduction zone east of New Zealand now extended south almost as far as Kaikoura, the seafloor continuing to spread, and the crust under the very high compression. We experience this today by numerous earthquakes. Only in the history of New Zealand, only in the last 20 years, we have numerous large and significant earthquakes. The whole history of New Zealand followed by big activity, not just along the Alpine Fault, everywhere. Every day there's earthquakes erupting around New Zealand. We recorded these all earthquakes, even the ones which are barely could be felt by people with equipment, and we know that yearly we have about 14,000 of the quakes occurring around New Zealand. Thus the Kaikoura Orogeny uplift of the Southern Alps started. We can tell that it started about 25 million years ago, when this collision occurred. Plate changes from ocean floor subduction to continental collision. A piece of land being uplifted along the fault and a place around the Kaikoura. We have this representation of high land uplifted along the faults, and the close inshore seafloor dives to the depths of 1,000 meters. The place where we have a lot of upwelling, the current going around that area, bringing colder, richer waters from the depth of the ocean, and this attract a lot of fish, mammals, sea mammals, and in particular the whales. That's one of the world famous places to sight the whales. However, the greatest uplift happening around the Southern Alps, further down to the east and south. Scientists suggested, although it all started 25 million years ago, but only the last 5 million years, we have this accelerated rapid uplift, which continues today. You can see on this cross section through Southern Island how the mountains being pushed up, how the Alpine Fault dips eastward at about 55 degrees, and the rocks at the west consist of granites and altered sedimentary rocks of Australian plate, while we see the schist to the east. And you can see the degree of schistosity throughout from the Alpine Fault eastwards. See the first video about Southern Alps when we talk about that. Scientists calculating the rates of seafloor spreading that the collision of the Pacific and Australian plates has compressed the New Zealand crust about 60 kilometers during the last 5 million years. Squeezing has gradually thickened the crust and pushed it up. Overall, the Southern Alps being uplifted more than 20,000 meters, about 20 kilometers. The material was constantly brought towards the Alpine Fault and uplifted, squeezed, pushed up. However, the erosion, such as water erosion, rivers, landslides, glacier activity, been removing that material and bringing back through the rivers towards the ocean. All this pressure is accumulated along this Alpine Fault and material around it during this long term, and as you understand, the properties of the rocks, they're very brittle. The property of the rocks, direction of the pressure and the movements of the plates, everything indicate of position of the faults, which we found today, and the Alpine Fault doesn't take all the pressure from collision of two plates, but it's also distributed into the adjacent faults that form all along, and especially towards the east. The Southern Alps, attributed to be one of the fastest growing mountains in the world, with a resulting uplift rate of 10-20 millimeters per year, which is mean that in a million years it will uplift about 10 kilometers. Geologists believe it has been accelerated only in more recent time, and then the bulk of the Southern Alps have been pushed up in the past few million years. Let's appreciate the erosion forces, which doesn't let the mountains be 20 kilometers high, but keep removing material constantly, piece by piece, rock by rock, in Southern Alps eroded away as fast almost as they've been rising. If you've ever been around Southern Alps in heavy rainfall or high flooding seasons, you will appreciate how much material rivers carry. And that's happening gradually and intensively during the events like heavy rainfall all the time. And geomorphologists and sedimentologists take over from the structural geologist and explain the features we see right now around Southern Alps. And that's where the very tricky part comes in place to understand which material moved from where, how much per unit of time, and what does it mean for Southern Alps. We'll talk about some erosion forces around New Zealand, and especially Southern Alps, because it's such a great example, one of the fastest growing mountains with enormous erosion. Stay with me, subscribe please, and like, comment on my video, so more people could see this video and explore the wonders of our planet.